Welcome to Mark's Tech Talk. This edition we're going to examine the idea of resonance in an electronic circuit. We'll start out with a series RLC circuit and try to examine to find what is the current. So you can review the previous video I've had on a series RLC circuit, but the short answer is we have to compute X of C, X of L, and then the total Z, and use that with Ohm's law. So first step is to find X of L, 2 pi FL, and we'll do that, and we get 15.7 ohms. And then we do X of C is 1 over 2 pi FC, and we're going to get 3.18 kiloohms. Now we're going to combine those two values along with the resistance in order to get the total Z. So Z of L is 0 plus J, 15.7, Z of C, 0 minus J, 3.18K, and Z of R is 2K plus J, 0. Now the total Z, we add the real parts, add the imaginary parts, and we get 2K minus J, 3.17K. Now we use Ohm's law to find the current, 10 angle 0 divided by RZ, and we get a value of 2.67, an angle of 57.8 milliamps. We're going to place those values in a table, and it looks something like this. Now let's do the same thing, but this time for 1 kilohertz. So I would suggest now you pause the video and go ahead and do your computation. We'll give you a moment, and then we'll go through the answers. Hopefully you have found that X of L is 31.4 and X of C is 1.59. Okay, and here are the values. X of L is 0 plus J, 31.4, 0 minus J, 1.59K for Z of C, and Z of R is 2K plus J, 0. And our values is 2K minus J, 1.56K. So now we'll do Ohm's law, 10 angle 0 divided by 2K minus J, 1.56K, and we get 3.94 at an angle of 38 milliamps. We'll enter that in our table. Let's continue that process for all of these frequencies. So find X of L, X of C, your total Z, and the current for all of these frequencies. And again, I would suggest pausing the video at this point. And then we'll go through one frequency at a time. All right, hopefully you've had time to do these computations. Following the pattern we did for the first two frequencies, for 2.5 kilohertz, you should have got 78.5 and 637 for X of L and X of C. And that gives you a current of 4.82, angle 15.6. We do the same thing for 5 kilohertz, 157, 318, and the current 4.98. One thing you can notice here, X of L is proportionate to frequency. So when we move from 2.5 kilohertz to 5 kilohertz, that is twice the frequency, so X of L is twice the value. So 78.5 multiplied by 2, you get 157. Now the X of C is inversely proportional to frequency. So as you double the frequency, the X of C should be 1/2. So 1/2 of 637 comes out approximately to 318. So you can use that proportionality instead of recomputing everything if you wish. It might make things just a little bit quicker for you. In any case, 7.5, that would be 3 times the 2.5. That would be 236, and then 212 for X of C, and a current of 5 milliamps. And 10 kilohertz, 314 and 159. And then 12.5, we get 393, 127. And 15, we get 471. And 106 for a current of 4.92. I did a couple additional frequencies. I didn't necessarily ask you to do these, but I just want to add those to the list. All right, let's take a look. What's happening with X of L? As we increase the frequency, the values of x of L are getting larger and larger. On the other hand, x of c starts out large, and as we increase the frequency, the x of c gets smaller and smaller. And notice at some point, those two values are going to intersect. In other words, they're going to be the same value. X of c is going to equal x of L at some point. And it's not real clear exactly where that point is, but you can see it's probably somewhere in the neighborhood of about 7 kilohertz. Okay, we don't know exactly, but again, somewhere in that neighborhood, 7.5 kilohertz. Okay, now if I were to plot the current, the magnitude of the current, I would get a plot that looks something like this. And you can see the current is increasing, 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 until we get right around that 7 kilohertz, and then it starts to decrease again. So what we want to know is, where do we get maximum current? What do we get maximum current at? Okay, we can see approximately where it's at from this graph, but we want to know exactly where is maximum current. Well, maximum current occurs when we have this condition we're going to call resonance. And resonance is when the magnitude of the capacitive reactance is equal to the magnitude of the inductive reactance. Remember, these are not equal because we have different signs here. The inductive reactance is a positive. The capacitive reactance is a negative imaginary, so they're opposite signs. But if we just look at the magnitudes, at some point they're going to be equal. And when they're equal, because they're opposite signs, they're going to cancel out. Once they cancel out, we wind up with a purely resistive impedance. And when that happens, that's when we get maximum current. So we want to know exactly when x of L is equal to x of c for our circuit. So we're going to plug in the value of x of L and x of c and solve for the frequency. So we rearrange that a little bit, and we get the frequency squared is equal to 1 over 2 pi squared times 0.1 micro times 5 milli. And then we'll take the square root and find that the frequency is 7.12 kilohertz. 7.12 kilohertz. So if we look on our chart, 7.1 is right about here. Okay. All right. So that's just under the 7.51. That's when a resonance occurs. That's when we get maximum frequency. And on the graph, that occurs right about here. And that kind of fits with what we had in the graph. That looks like it is the maximum right there. All right, so in general, resonance occurs when x of L is equal to x of c. So these are our generic formulas for x of L and x of c. We set them equal. We solve that for the frequency. And what we get is we get frequency is equal to 1 over 2 pi square root of L times c. All right, that's the resonant frequency, 1 over 2 pi square root of L times c. Very, very important formula. You really should memorize that formula. You'll be seeing that quite often. All right, so very important formula. I tell my students to take that formula, write it down, and put it under the pillow at night. Help them memorize. Some of them actually have supposedly done that. They've sent me pictures. So anyway, remember that formula. It's an important formula. Okay, so let's take a look here at what happens in our circuit at resonance. Frequency is 7.12 kilohertz. So let's find the current at resonance. So we'll figure out the values of x of L at resonance. Okay, 2 pi times 7.12 K times 5 mil for the x of L. That works out to 224. We'll do the same thing for x of c, 1 over 2 pi, the 7.12 K and the 0.1 micro, and that works out to 224. Remember, that's the idea of resonance. The magnitude of both x of L and x of c will be the same value. So what happens now when we add the z's is the x of L and the x of c cancel out, and we're left with just the resistance of 2K. So the total Z is 2K minus J0. So our current is 5 milliamps at an angle of 0 at resonance. All right, so here's a circuit that we have at resonance, the same one we started with. 7.12 we figured out is the resonant frequency. We found the current. Now let's find the voltage across VC, VL, and VR, again at resonance. So we take the current and multiply by the Z of each component, just Ohm's law for each component individually. So V of L is the current, 5 milliamps, angle 0, times the Z of the inductor, 0 plus J, 224. That gives us a value of 1.12 and angle of 90. We do the same thing for VC, and we find VC is 1.12 angle minus 90. And then we do VR, and we get a value of 10 angle 0. Now, if we were to do Kirchhoff's voltage law, add up all the voltages around the loop, we'd have a source voltage of 10 angle 0, and then the inductor and the capacitor. Notice the inductor is an angle 90 and the capacitor's angle minus 90. They're going to cancel out, and therefore the sum of the voltages will equal 0. Okay. All right, so here is another circuit. We want to find the resonant frequency, different values this time, 10 millihenries and 0.5 microfarads. So we plug those into our formula, 1 over 2 pi square root of LC, and we find out the resonant frequency is 2.25 kilohertz. 2.25 kilohertz for this particular circuit. All right, here's another one, 8.2 microhenries and 0.022 microfarads. Find the resonant frequency. And again, pause the video, try this out for yourself, and see if you get the right answer. Did you remember the formula, or did you have to look it up? The formula for resonance is 1 over 2 pi square root of L times C. Plug our values in, and you should get 375 kilohertz for the resonant frequency. 375 kilohertz. All right, now let's try it a little bit differently. This time I'm giving you a resonant frequency, 3.5 megahertz, and the value of the inductor, and I want you to find the value of the capacitor. So I have to do a little bit of algebraic manipulation here. Okay, so taking the formula, we'll plug in the values. I find it a little bit easier to put the numbers in first before I solve for the unknown. You can solve for the unknown first if you are comfortable with algebra. A lot of people find this a little bit easier to do. And I rearrange it a little bit and solve for C, and I get 304 picofarads. 304 picofarads. Okay, so that's a brief introduction to the idea of resonance. Hope you enjoyed this, and stay tuned for more videos on Mark's Tech Talk. Thank you for watching.